Okay, class. I'm going to intro a little bit of an assignment here, kind of a little in-class activity that'll probably take a day or day and a half or so. It does require a little bit of explanation as well as a little bit of background. So previous to watching this video, hopefully you guys should have gotten passed out. If not, please pause the video and do this. The Keplers Law activity questions, it says that at the top, should look like this, the first page. And then the other two pages look, like this, and then there's a graph thing. So make sure that you have that in front of you before you watch this video. So, we watched a video yesterday about Kepler's 3 laws of motion. So I quickly want to revisit that, make sure that we understand it very quickly. Okay, so just a little bit of lecture here. So for a long time we thought the motions of the planets, scientists thought they were all circular. We realized eventually that that was not the case. Johannes Kepler, a scientist I believe from the 1600s, realized, figured out how to predict the motion of all the planets, where to find them in the sky at all times. And he found 3 laws of planetary motion to define those things. He said, Kepler's first law said the paths of the planets are ellipses. Now remember, an ellipse is like kind of an elongated circle, kind of like an oval, like you see down here, with the sun at one focus. So this is an exaggerated version of what any of the planets look like. Most of the planets are very nearly circular, but ever so slightly eccentric. So the sun at one focus, on the video from the other day, they talked about connecting a string between 2 pins and dragging your pencil around. And that's kind of how you make an ellipse. So eccentricity is a term that's like a measurement of how elliptical something is. The larger the eccentricity, the more it looks like an oval. The lower the eccentricity, closer to 0, the more it looks like a circle. We can quickly go to an animation here where we see that. Sorry, here is an animation where we see that. So we're looking at Kepler's law here. Okay, you have the sun. We can run this animation. So here's like the orbit of Mercury. Mercury is pretty elliptical. And we can start the animation. Slow the animation down a little bit. And we see that. We can also show the empty focus there. The sun's at 1. The other one is an empty spot in space. So right when Mercury is over here, that is when it's closest to the sun. When it's over here, that is when it's furthest away from the sun. This is what you'd call aphelion. This is what you'd call perihelion. A for away, aphelion, A-P-H-E-L-I-O-N, and perihelion with a P over here. And we could set parameters for all the other planets. Now most of the other planets all have an eccentricity very close to 0. We can see that here. Venus, 0.007. Earth, 0.017. Very, very low eccentricity. Mercury, if we go back to that, 0.2. That's kind of a high eccentricity. Pluto also has a high eccentricity. That means it's really elliptical, 0.249. Pluto is higher than any of the other planets. Mercury is really the only other planet that has that there. Okay, so that was Kepler's first law. Kepler's second law, we can do this here. We'll come back to that animation here in a moment. But Kepler's second law says, it's kind of a weird one, that an imaginary line drawn from the planet to the sun will sweep out equal areas in equal time intervals. So you have the sun here, you have the orbit of a planet going around it. Now if you draw an imaginary line from the sun to that planet, and the area that that planet sweeps out for any equal time intervals are always going to wind up being equal. Again, we can wind up going back to this. So here we look at Mercury. There's one period of time. There's another period of time. So if we look at there, okay, this area, this shape does not look exactly like this shape. This is long and skinny, and this is short and wide. Now, what Kepler's second law really says, it's kind of a weird way to explain that the planet moves faster when it's close to the sun and slower when it's further away. Again, it's close to the sun here, so it travels this much distance in that amount of time. Over here, it only travels this much distance. a much shorter distance. So say this is what we plotted it for, I don't know, 3 days or something like that. In 3 days, Mercury traveled this much distance, and 3 days, Mercury traveled this much distance. Those distances aren't equal, but the area that is swept out by that imaginary line winds up being equal. And we could do the same thing for any other equal time interval. And all of these areas are equal. That's what Kepler's law says. Kind of makes a fun little pattern here. Now, if we pause that animation and just make a hypothetical planet, so no planet is this eccentric, but if we start that animation, we can see how slow it's moving, and it zips right around and makes a totally different shape. I'll catch it when it's a little bit closer. Sorry about that. Need to be a little bit quicker. But see it zip around when it's close, slow when it's far away. And again, we could select any other period of time, but these areas are all equal for any equal time interval. And this is a weird way of explaining how a planet is moving slow. Its orbital speed is slow when it's far away, faster when it's close. And that's true for every planet, and this law explains how that works. Okay, so again, eccentricity goes from 0 to very close to 1, but something that has an eccentricity of 0 would just be a full circle. So all of these shapes would be the exact same shape if we're talking about just a perfect circle for a hypothetical planet with an eccentricity of 0. Then Kepler's third law is the one that has kind of an equation associated with it. Okay, it relates orbital period to orbital radius, and it's a comparison between two planets. So the orbital radius of, say, planet A compared to orbital planet B, say Mars and Jupiter, squared is compared to their orbital radiuses cubed. Okay? Now, we don't like to do a whole lot of math in here, but we need to understand what this equation means. What this equation means is that for every orbital radius, think in terms of AUs, for every orbital radius, that orbital radius has a associated orbital period with it. So the Earth is 1 AU away from the Sun. That's its orbital radius. That'd be number 1, right? Its orbital period is 365 days. That means if there was a magical planet X on the other side of the Sun, that's the exact same distance away from the Sun, 1 AU away from the Sun, that means that its orbital period would have to be the exact same as Earth's. It would also be 365 days, which means, weirdly enough, we would never see it because it would always be exactly opposite the Sun as us. If it's the exact same distance away, at that distance, it has to take the same amount of time to orbit the Sun once. And again, you get all these squares and cubes and stuff, and it gets really complicated. But don't overthink it. It essentially just means that for an orbital radius, a planet has to have a known orbital period, and it's related by this ratio here. If we wind up using the orbital period of the Earth in years, that's 1. The orbital radius of the Earth in AUs is 1. So once you start putting 1s in this equation, it gets a lot simpler. Okay, so that's Kepler's 3 laws in a nutshell. That's probably it for the notes, at least until I get back. Okay, so now look at the handout. Go to the last page of your handout. It should be a piece of paper that looks like this. Okay, rip that page off and hold it on your table like this so that the 0 is on your right hand side. Okay, I'll give you guys a second. Rip that off, place it like this. Okay, you're going to be plotting the orbit of Mercury on this really weird looking graph paper. Okay, now what are you going to be plotting on there? On here, you're going to be plotting this data, the stuff on the back of the front sheet. Okay, so look at this table that is on the second page. It says 58 at the bottom or whatever. But this is the orbital data for Mercury, for one orbit of Mercury. So we took a bunch of dates, 1990, from October 1, 1990 to December 30th of 1990. Tells you the orbital radius in AUs of Mercury and how it changes, and it also gives you the longitude. It's kind of like an angle. Okay, so each of these data points you are going to plot on this graph paper. So if you look at this first data point, see if I can get both these things on the screen at the same time. Okay, so this first data point is 0.319 AUs, 114 degrees. Okay, this can kind of be confusing for people, so make sure that you guys pay attention here. So, on this graph paper, you guys probably aren't familiar with this, but here's 0 degrees, 10, 20, I know there's two sets of numbers, but look at it this way, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, all the way to 180, to going this way, 270, back to 360. Okay, so this is the way we're looking at it. 0 to 90 to 180 to 270 to 360. So your first data point, it says 114 degrees. 114 degrees is over here. So here's 90 degrees, here's 100, here's 110, and then 1, 2, 3, 4. So we're going to be like right over here. We're going to be right in this area, 114 degrees. So you are going to be drawing a point going from here in that direction. Well, where along this line do you draw it? You draw it on this line this far away. Okay, so remember your radius vector. This is in AUs. Now we need to make this a scaled drawing. So let's use your scale as every 0.1 AUs, 0.1 AUs, so 0.1 on here is equal to 1 centimeter. So you're going to need your rulers. So your rulers are in the orange box over by the basketball hoop on the left side of the room. So 114. So that means that you're going to measure 3.19 centimeters out from here in the direction of 114 degrees. So these circles kind of line up with that. So this is 1, 2, 3.2. So this first one is going to be drawn, it's kind of hard to do this on the computer, but about right here. I can't draw on this slide, but about right there. So it's going to be 3.2 centimeters out from the center towards 114 degrees. Then the next one is going to be at 126 degrees. So just slide your ruler over to 126 degrees. 126 degrees is over here. So it's going to be somewhere along this line. But this one is going to be about 3.3 centimeters. 3.3 centimeters out from the center around here. Okay, so draw each of these data points. There's two columns here, remember. So this whole column here. So this whole column here is 1. And you got to do this whole set of data over here. Okay, so it was November 14th, then it picks up to November 16th over here. I know it's kind of annoying, but you'll have plenty of time. So just keep scooting along, drawing. You know, it should wind up being a nice, smooth ellipse. The center is going to represent the sun. This little center point here represents the sun. Each of the data points that you're drawing represent Mercury at different positions. Okay, represent Mercury at different positions. You should wind up with a nice, smooth ellipse. It shouldn't have these weird jagged parts all over it. It should be nice, smooth. So I know the measurement's a little weird, but remember, look at the degrees and draw that many centimeters out. But remember this scale, 0.1 AU over here, this one is going to have to be drawn, it says 0.319 AUs, so it's going to be drawn 3.19 centimeters, or run at 3.2 centimeters out from the center towards 114 degrees. Okay? Mr. Lovett can replay this for you again if it gets confusing. But it should really look pretty good. It's if you're listening, it's not that complicated, And it can kind of go kind of fast. You just scoot the ruler over to the next degree mark, measure that centimeter away. Okay. Okay, so once you've completed the full ellipse, also notice that you complete a full ellipse when you get back to the same degree measure. So you start at 114 degrees, so the circle or the ellipse is completed when you get back to here. In a later part of the assignment, you're going to have to count the number of days. So you're going to count the number of days from here all the way to here. You get back to where you started by the time you get here. It just goes a little overlap there. So again, double check that you get a smooth ellipse going around the sun here. So then from there, we're going to use that data to kind of confirm Kepler's 3 laws. So after you draw that, you plot that out, you're going to go to these questions. Some of them are pretty simple, some of them are a little bit more involved. Just make sure you listen to instructions. First one's pretty self-explanatory. Second one's pretty close to is pretty self-explanatory. On the third one, you have to do a little bit of math. So you can use a calculator. Just make sure you're doing it right, because you have to square some things. Okay. So again, 1 and 2, pretty self-explanatory. You guys can do that. So you get to 3. It says, how long is Mercury's orbital period? The amount of time it takes to complete one full time around the sun. Use your table that we were just looking at to count those days. So when we are looking at our table, that is this table. So you're going to count the days from here to when our circle completed. So that is on the December 28th. Make sure you know that each data point is 2 ways away. So you're going to have to do, 31 days, 31, 32. So for each data point, you're going to have to count 2 days. So 3, 5, 7, and so forth. And just that number is going to go there. For B, find Mercury's average orbital radius by finding the longest orbital radius and the shortest and averaging them and write it below. Okay, we're going to use this in Kepler's third law. We're going to use its average orbital radius to try and confirm Kepler's third law. Now, I did make an error on the sheet, so listen very carefully because there is one step that you have to write in here. Okay, so after you write that, we're going to call this just, part B2 is then take that number and cube it, meaning take it to the third power. So, one of these guys, the up caret 3, to the third power. You have to do that. That was an instruction I forgot to include on there, but you're not going to wind up getting the right result. So make sure that you write that in there. Everybody write that in your sheet. Take that number and cube it. Take it to the third power. So if the number was 2, it's not going to be 2. It's going to be 2 times 2 times 2. It's going to be more like 0.4 or something around there. It's going to be 0.4 times 0.4 times 0.4. Okay, to the third power. Okay. So I already wrote that in this edited version here. So just to reduce confusion, I'm going to reduce that. So what it looks like on your sheet still looks like this, but this part in bold here is the part we had to include. So multiply the number you found in B, but in B2. Multiply that number after you've cubed it by 365. So again, write that in there, and you have to multiply by 365 squared. When you do exponents and squares and cubes and stuff, it's easy to screw it up in your calculator, so double check you're doing it right. Multiply the number you found in B2 by 365 squared, okay? So, again, the part in bold here, those are things you have to write in. Those are instructions I forgot to include in here. Make sure that you're listening now and re-enter those 2 things. Okay? So, then you take that number and find the square root of it and write it below. Now, it says to compare the letter D from the letter for A. Now what we're trying to do is, if you look at F here, those numbers should wind up being the same. Okay? I took you through doing the whole Kepler's third law equation. Okay, remember Kepler's third law was this. I'm taking through it stepwise so you don't have to think too much. But you have to the goal here is that if these two numbers are about the same, within 1 or 2 of each other, that's kind of confirming Kepler's third law, okay? And it relates the two values that we get from here. Remember, this is orbital period. That's how long it takes to orbit. And this is orbital radius, or average orbital radius, for one planet compared to another. What you're actually doing here is comparing Mercury's orbital period to Earth's. That's why we use the 365. 365 is the Earth's orbital period. The Earth's orbital radius in AUs is just 1. Okay, so this number 3 here is just me kind of taking you through the steps of solving the equation for Kepler's third law. If your answers for A and D here are not very close to being the same, within 1 or 2 days of each other, then you did your calculation wrong. But please, again, make sure that you include these edits. Otherwise, you're not going to get that. So again, you need to be paying attention and make sure that you have to include these extra steps here to get the right answer. And we're looking to see that what you got in A and what you got D is about the same. Otherwise, you did it wrong and you're going to lose points. So 4 is more of just a logic question, making sure that we understand the force of gravity. Here we call aphelion versus perihelion. And 7 is one last step. So 7 says color in the line swept out by a line from the sun to the Mercury, 2 different 10-day periods. Do the shaded regions look like they have the same amount of area? Which of Kepler's laws said this? So you're kind of on your sheet, on your graph sheet that looks like this, that now has a big old ellipse on it. You're going to kind of draw, you know, these sweep out areas. Is that you're going to have 2 different 10-day periods, and you know, Mercury has a little bit more eccentricity than that. Mercury has an eccentricity about, 0.2. So this is Mercury here. You're going to have, draw 2 different 10-day periods. You can use that, again, using your data sheet, and see roughly if these 2 areas wind up looking equal to each other. Okay, so again, if you need to replay a few parts of this video to understand, that's fine. But drawing the orbit of Mercury should take a little bit of time. But once you get used to it, it should go pretty fast. Okay. Again, you just kind of keep scooting your ruler and working that out, the right number of centimeters to the right number of degrees. Again, the picture here should be a nice smooth ellipse, and your answers on this sheet should be, what we're hoping for. Okay. So answer these as best you can. This should take you the rest of the class period today and into tomorrow a little bit. Good luck, and I'm sure Mr. Lovett can help you if you need to. This will be an activity we'll be doing later on. Maybe when I'm here, but maybe not. We'll see.